Hello, everyone. It's my pleasure to introduce the speaker today, which is Matt Dannenberg, who's going to talk about renormalization.
Hey, everyone. So I'm excited to talk about renormalization today. It's a topic I'm really interested in, so I think it'll be interesting to share. This renormalization is an idea that pops up in a lot of different guises in a lot of different parts of math and physics. So what I'll try to do is in the first part of the talk to talk a little bit about what renormalization is, what it means for it to sort of act on a space, and how a proof using it actually works, and what it has to do with self-similarity. And then from there, I'll spend most of the time of the talk discussing how it relates to the dynamics in the circle map case. So dynamics of maps of the circle. So first and foremost, let's start with what is renormalization? How does it act on a space? So I've written out this sort of vague kind of definition, which is a renormalization operator on a domain D is a map from some subset of the domain to itself, which represents zooming in to a new scale, and which preserves some kind of normalization in this domain. And I'm being intentionally vague about what these mean because they can mean a lot of things. As a dynamicist, whenever I have any kind of operator, I want to iterate it. So by iterating this zooming in operation, we hope to understand some kind of global information of the space based on the fixed points of R. And so in a sort of broad sense, the idea is that we'll have some space of normalized things. We'll perform some kind of rescaling map, which will give us a rescaled thing. And this thing usually will not satisfy whatever normalization criteria we choose to impose. And so we'll apply a second operation, which is normalizing. And this gives us something which has been re-normalized, which is the origin of the term. And so this idea fits into sort of a lot of different contexts, because if something is a fixed point of this, if I can zoom in on it and it looks the same, then we say that it's self-similar. And more or less, whenever you see the word self-similar appear in math or physics, there is probably a secret renormalization thing operating in the background, some more interesting than others. So let's talk about this in the context of probability. So let's look at a probability space, omega, with some sigma algebra and probability measure. And what we're interested in is the space of random variables, which is to say measurable functions into R. All you need to really think about here is just think about these as distributions on R, probability distributions on R, with finite mean and variance. Okay, and so the question is, I mean, when I've defined this space, it's not even obvious that there is a notion of scale, let alone that I can change it. So what does it mean to zoom into some sort of new scale in this space? Well, so what we'll do, what we will do when the tablet's not fighting me is, so if I take, x some a random variable, so let's look at the sequence of all discrete times 4. What I can do is think about a sort of process where what I'll do is I'll start at 0, and at every integer moment, I will randomly generate a number according to this probability distribution. So maybe my first number I'll call x1, which I'll generate according to x. And right here, at a moment 2, I'll generate another number, x2, and I'll plot x1 plus x2. Maybe at moment 3, I generate another number, x1 plus x2 plus x3. And I can keep going on and on and on. And this is a model of a random walk. But the random walk itself doesn't really matter to us. This is what allows us to define a notion of scale to this random variable. And so our rescaling operation is very simple. Instead of generating something every 1 second, and then we'll count and counting our time in terms of the number of samples, we will instead generate something every 2 seconds. And we'll count our time in the number of pairs of samples. So time is shrinking by a factor of 2, and we're just generating 2 random variables at once instead of 1. And so in this sense, our rescaling map is R, not script, x on x by x1 plus x2, where x1 and x2 are independent with the same distribution. As X. And this is well defined as a map on distributions. Okay, so this we call the rescaling map, or a rescaling transformation. So again, I'm a dynamicist, so my next question is always going to be the same, which is what happens if I keep applying this? So what happens if I consider the nth iterate of X? And if you're not familiar with dynamics notation, this means R composed with R, composed with R, composed with on and on, n times. Well, if I apply it once, I'm adding up two things. So if I apply it n times, I'm just adding up 2 to the n things. So sum I equals 1 to, not n, 2 to the n of xi, where all of these things are independent and identically distributed. So what I can do then is I can ask some simple questions about the statistics. What happens to the mean? Well, if I add up 2 to the n independent random variables with the same mean, the means just add. So this is equal to 2 to the n times the mean of x. Likewise, the variance sigma squared of Rn x, well, this likewise variance adds for independent random variables. So I have 2 to the n times the variance. And so the important thing for me is I want to know what the limit as n goes to infinity is. And in both of these cases, this limit is infinity unless there's 0. And so my space of random variables had finite mean and variance. And so what we can tell immediately from this is that there is no limit unless both are 0. And if both are 0, our probability distribution is a delta function at 0. So this is not the most interesting operation. You take something and if I apply rescaling a whole bunch of times, I'm just generating so many random variables that I basically instantly go to infinity, which is not interesting. So what we need to do is introduce some kind of normalization into this space. And our normalization here is will require that the mean is 0 and that the variance is 1. And the important thing to note is that R does not preserve this. I mean, it preserves the mean condition, but it doesn't preserve the variance condition. If I rescale something here, the variance will be 2. And so it's no longer in this class. But what I can do is to very simply just multiply by something to make it so that now, so my renormalization operator will be the rescaling times something that makes it so that the normalization actually holds. So in particular, this is 1 over root 2, x1 plus x2. Okay. Yeah. Okay. So this still preserves. So now this operator actually takes things that satisfy this normalization condition, and it maps them to things that still satisfy it. Yay. So we can ask what happens if we iterate this. So this is now a script R, which I will struggle to write throughout this entire talk. So forgive me for that. So if I apply this n times, well, I'm multiplying by 1 over root 2 n times. So I get 1 over square root 2 to the n times, and then I'll just be adding up, again, these 2 to the n random variables. Okay. Now, if you remember your probability, this expression probably looks a little bit familiar. I'm adding up a very large number of independent, identically distributed random variables, which have mean 0 and variance 1. And I'm dividing by the square root of the number of things I'm generating. This is the setting of the central limit theorem. So the central limit theorem tells us that sums of this sort ought to go to a normal distribution. And so in terms of what we've written, if instead of n, I take 2 to the n in this expression, this tells us that we should expect a certain limit behavior for this. Rn of x should go to a normal distribution. And even more than that, we can say that R applied to a normal distribution, well, it ought to be equal to a normal distribution, because it shouldn't move away from itself. Okay. So the power of the renormalization method comes in not thinking about this as a sort of geometric operation, this rescaling, but to think of this as some operator on the space of probability distributions, or whatever space it's acting on. And so the question is, can we actually prove the central limit theorem with this idea? And the answer is actually yes, but it's hard. So let's go through how we would do this. So to make our lives a little bit easier, I'm going to make it so that my random variables are absolutely continuous with respect to Lebesgue measure, which is to say they just have probability densities. And I'll think about renormalization as an operator on densities instead of on probabilities, or on some sort of abstract measure. Okay, so remember, just to keep it in view, that R of x is equal to 1 over root 2 x1 plus x2. Okay, so what I want to do is I want to figure out, can I write q of x in terms of p of x? Well, what if it was discrete? If space was discrete, I'll try to motivate this formula a little bit, because the first time I saw it, it was not so obvious. So if space was discrete, well, we could say that think about q of x as the probability that y is equal to, that capital Y is equal to lowercase x. If space is discrete, then q of x ought to be equal to the sum of y plus z equals x times root 2 of p of y, p of z. It ought to be equal to the sum of the number of ways that I can combine something with probability distribution, two things with probability distribution p, add them together, and get x times root 2. We'll pause for a moment to let that sink in. So, of course, in this expression, z is superfluous. I don't need it. So I can just think of this sum over y of p of y, p of x root 2 minus y. Okay. And so all that changes if space is discrete is that instead of the sum, I write an integral. So r of p of x is equal to q of x is equal to the integral from minus infinity to infinity of p of y times p of x root 2 minus y dy. Now I've lied a little bit. There's actually a multiplicative factor here. See, because q ought to be a probability distribution, so it ought to, if you integrate it, it ought to be 1. And you can actually find this constant. It's just root 2. And this is our renormalization operator. So this operator, now that we've written this is a nonlinear, it's quadratic operator on an infinite dimensional space. Which is to say, this thing's awful. But in this case, it's actually not so bad. I won't deal too explicitly with it, but these are, if we wanted to prove the central limit theorem from here, now that we have our operator, we just need to verify a couple of properties about this operator. So the first thing is that the density of the normal distribution is the only fixed point. I'm not going to do this calculation that it is a fixed point. It's not a very difficult integral. You can just substitute in and you'll get that this actually is a fixed point. Only is a bit of a hard one. But I'll address that in a moment. So let me table that discussion of only for a moment. But it is indeed a fixed point. The next thing is that we want to know that the linearization of the operator at n01 at the normal distribution has all eigenvalues strictly less than 1, which is to say that the differential of R restricted to the tangent space at n01. What I want is this is a linear contraction. So I mean, all you need to do here is just compute the eigenvalues and just say they are all less than 1. In this case, actually, despite the fact that this operator looks bad, you can actually exactly find every eigenvalue and eigenvector of it. They have to do with Hermite polynomials. So this is actually you can solve this exactly.
With what polynomial, sir?
they look like Hermite polynomials times Gaussians, the eigenvectors. This is actually an operator you can do this exactly for. That's not always true in renormalization, but here you can do it exactly. And the last thing is that actually R is a contraction. So in this case, this nonlinear operator is actually a contraction, and so the only here that is the only fixed point is an immediate consequence of this, because there can only be one fixed point if we have a strict contraction. And I mean, I haven't actually verified any of these things, but I don't want to, so I won't. This is a proof of the central limit theorem with renormalization, which is, I think, cool in its own way. Okay, so I mean, what is my point in mentioning any of this? Is that fixed points of renormalization operators and their stability, and perhaps some global properties of the operator, tell us a lot of information about some sort of global structure on a space. Here, the central limit theorem is global information about how probability distributions behave, and we invert it from based on some sort of rescaling principle. Now, in this case, we already knew the theorem, so I didn't really need to do much to talk about it or manually find points. We may not always know the underlying theorem. So with that, let me sort of move into talking about this in dynamics. You can play similar games with this rescaling, define your own situation with rescaling, and come up with some arbitrary normalization, and you can actually come up with a lot of theorems this way. You can play the same game with the law of large numbers if you pick your normalization cleverly in the same space, or not even so cleverly. Okay.
Sorry, can I ask a question?
Yeah.
What does it mean, the differential of the operator?
I mean, it's derivative.
Right, but like, isn't this like an operator on some infinite dimensional thing?
Sure, but I mean, like, just like anywhere else, right?
Is it still like a manifold or something, or?
It is still a manifold. So dr of.
So the space of measures is like a manifold.
It is in fact exactly a manifold. So I mean, it acts on vectors v is the what is it r of n plus v minus r of n over.
Oh yeah, okay. Thank you.
Yeah, I mean this I mean,
no, that's good. Thanks.
Yeah, these operators are normally analytic, and so more or less any definition of derivative you want to define will work.
Okay, thank you.
Yeah, so these it's an important point. I mean, I think that one of these previous talks in the seminar, I think, was on infinite dimensional calculus. So stuff does get kind of thorny, but at least in nice situations, this tends to not bite us. And any other questions before we move on? Okay, so now I'm going to talk a bit about dynamical systems. And so I understand that perhaps a lot of you have not seen much dynamical systems. So let me just briefly talk about what kind of question are we concerned with. So in dynamics, we're really concerned with is the behavior of maps which go from some object to itself, usually topological or theoretic, some sort of space to itself. And what I would like to know is things like how many possible ways can F behave or act on this space. And in particular, in dynamics, we often do this by analyzing the behavior of Fn, some iterates of F. And using this sort of thing, we can hope to understand what the different ways that F behaves. But the important thing is that if I'm doing this sort of behavior, if I draw, you will increasingly notice as I go through this talk that I tend to draw in rainbow. So forgive me for that. So imagine if I have two maps acting on a space, F and G, and I can ask, when are they acting the same? What does it mean for them to be the same? Well, it means that there's a change of coordinates on X that turns F into G. And this is just, this condition is literally just that this diagram commutes. So F and G are the same if this diagram commutes. And this is the same thing as saying that H composed with F composed with H inverse is equal to G. You should think perhaps by analogy with this, if you're not familiar, this is the same thing as like when you diagonalize a matrix, A equals PD P inverse, that if you understand immediately all powers of A as all powers of D once you have this sort of relationship. And it's the same thing with commutation. Once you understand a commutation relationship, it holds for all powers. And it tells you that the way that F is acting is the same as the way that G is acting. And so this is a big problem in dynamics, is how can we classify things up to conjugacy by some map H. Okay, and this is the sort of thing I'm concerned with here, actually. So the main idea, so renormalization is always about self-similarity. Self-similar things are fixed points of renormalization operators. So in dynamics, self-similarity has to do with this sort of picture that I will draw and hopefully a chance to explain later. So if I have some space X where F is acting, what I want is some subspace Y, some smaller space Y, such that when F acts, it gets sent somewhere, and then F acts again, and it gets mapped ultimately onto itself. And the hope is that the dynamics on Y, which is to say the dynamics when you start in Y and you wait until you come back, dynamics on Y, I want it to heuristically looks like the dynamics of X. And I'll try to get into detail a little bit later about what exactly I mean by this. But I want something that looks like the dynamics of the whole thing. Okay. So here's the sort of goal theorem. We'll see if I actually have time to get here. But the goal theorem that we're going to try to prove with renormalization is that every analytic orientation preserving diffeomorphism of the circle, which is to say some F in this class, with sufficiently irrational, and I'll get at what I mean by this, rotation number rho is up to an analytic change of coordinates, the same thing as this rigid rotation. So this is a map on the circle where it just takes the whole circle and rotates the whole thing by a single angle. And moreover, any generic one-parameter family of diffeomorphisms of the circle, say just a family of functions, will contain only isolated elements with that rotation number. So this is the theorem we're going to sort of aim for, but this is full of words that I haven't defined. So let's start by getting there. And most likely, time permitting, we'll get here today during this talk. Okay. So first and foremost, I need to define rotation number. If you're not familiar. So let's consider a map of the circle. And so for any lift to the universal cover, we're going to define the rotation number to be equal to this limit. So this is the limit of where I apply the lift n times to x, and then I subtract off the point I started, and I divide by n. So what this means, this is the average amount of rotation per application of f. It's on average, how far around the circle do I rotate every time I apply the function. And I claim that that this limit exists, that it doesn't depend on x, and that if you take it mod 1, it doesn't depend on the lift either. And I also claim that the map has a periodic point if and only if this limit is rational. So let's prove this, because I got to prove something, otherwise it's not a math talk. So first and foremost, let's talk about the independence of lift. Okay, so there's two properties I've written here which are of use to us. So for independence of lift, this property is our important one. So this says that if I lift my circle map to R and it's a diffeomorphism, that if I go up by 1, then the lift increases by 1 as well. So this is to say that if I zoom out really far, all lifts of the circle look kind of like lines with slope 1. If I zoom out really far, they all look basically like lines. Okay. So for independence of lift, all that we need to do to show this is that f hat. So suppose f hat and g hat are 2 lifts, then their difference is just a deck. They differ only by a deck transformation, and deck transformations are just integers. So in particular, that means that nth iterates, well, using this property, nth iterates differ just by n times whatever integer they differ by. I'm just adding k every time I apply it. Okay, so that means if I look at my limit above, the only cost in this limit to replacing f with g is that I've just added k times n. And so I'm just adding k to the limit. I'm just adding an integer to the limit. So we only add k to the limit. So I claim that if I don't care about adding an integer, this doesn't matter. So the next part, independence of x. And for here, we're going to use this property that lifts of circle diffeomorphisms, which are orientation preserving, preserve order. So for here, what I'll note is that 0. So let's pick x such that it's between 0 and 1. Since I can just translate it by an integer, this isn't really an assumption. So this means that, well, we'll just apply f n times. Okay, so if I apply f n times, this order preserving property means I have this inequality, and I've written it wrong. There we go. But the nth iterate of f on 1, well, that's just 1 plus the nth iterate of f on 0. And so now I can just do everyone's favorite trick where I rewrite something by adding 0. So fn of x minus x over n is equal to f hat n of x minus f hat n of 0 plus f hat n of 0 minus 0 plus 0 minus x. And I can write out the fractions. This fraction, the numerator is bounded by 1 by what I just wrote above. Divide by n goes to 0. This fraction, the numerator just doesn't depend on x. Divide by n goes to 0. So that means that if I take the limit, in the limit, the only 2 terms which matter are this one and this one. And so they have the same limit. So limit at x agrees with the limit at 0. Okay, and so that's true for all x, so it doesn't matter what point I pick. This property is also like, this property is kind of magic for circle maps. This doesn't work in like any other manifold with any kind of nice invariant of this sort. Okay, and so for the last bit, I've argued all these independence properties, but I haven't actually told you the limit exists, which is mea culpa. So let's talk about existence and rationality, and I'll try to prove them both at once. So I guess let me scroll up for a second. I haven't told you, if you're not a dynamicist, I haven't told you what a periodic point is. So a periodic point means that this is an x such that there exists k greater than 0, such that fk of x is equal to x. If I apply f to this point a bunch of times, the point actually comes back to itself. Okay, so what I'm claiming is that the map has a periodic point. This happens if and only if the rotation number is rational. So let's suppose we have one. F has a periodic point x in S1. So that means that fk of x is equal to x. So now if I pass to the lift, that means that f hat applied to the lifted point corresponding to x, well, this is going to be equal to x as well, possibly up to adding actually, I wanted this to be an n. Possibly up to adding some integer k. And what I claim is that, well, the rotation number means it's the average amount I go around the circle every time I apply f. So this equality tells me if I apply f n times on this point, I go around the circle exactly k times. So this means that that this limit rho, this rotation number, is just equal to k over n. It's rational automatically. On average, every time I apply f, I go around the circle k over n times. Okay, so let's suppose then that f has no periodic points. And I'll cheat a little bit on this one, but if f has no periodic points, then this tells us that for all k and n, either for all x, f hat n of x is greater than x plus k, or for all x, f hat n of x is less than x plus k. Because if it was ever equal, we would have a periodic point. So one of these two cases holds for every single pair of k and n integers. So let's just suppose for the moment that the top case holds. Top case holds. The top case implies, so I guess what I claim is that the top case implies that rho is strictly bigger than k over n. Seeing that it's greater than or equal to is somewhat clear in some sense, because we're moving further than k over n every time we apply f. Seeing that it's strict is not so obvious, but I don't want to prove it, so I'm just going to tell you that this is actually true. Okay, that this is actually true. So now consider the set of k over n such that the top case holds. What I claim about this set is that if a rational number is in it, then every rational number less than it is in it. And so in particular, this is the Dedekind cut, which you may remember from way back when in your first analysis class, when you completed the rationals to get a real number, that we identify real numbers as Dedekind cuts, which are just these sets of rational numbers, all rational numbers less than something. So in particular, this Dedekind cut is equal to rho. So in this way, this is the limit. So this is the existence of the limit, and that it's irrational whenever you don't have a periodic point. Okay. Questions?
How are you defining the set?
How am I defining? This is
The kns.
What's that?
Sorry. For every k and every n, either you have the top case or the bottom case.
Yes.
Right?
And so I am just defining this as the set of I guess it's not so clear that if it's not immediately obvious that if I take 2k and 2n that this still holds in the same way, but you can apply if you apply f hat n again to this expression here, it's somewhat clear that like multiplying, for example, by some number, both k and n, doesn't affect this. So this is actually well defined as a set of rational numbers.
Okay.
Thanks. I am skipping details, but uh-oh, no, that's not what I want. Okay, well, there you go. Okay, so let me just mention a couple of other useful properties of this that sort of follow from definition in a way. So first, if I think about the rotation number as a map from circle maps to R mod z, it's continuous. If I change the function only a little bit, rotation number changes only a little bit. And this is somewhat clear from it being as described as this limit. Not entirely obvious, but the other thing is if I take my map of the circle and I add something small to it, I take my map of the circle and I add something small to it, I'm going to increase the rotation number. If I make the map bigger, it rotates faster. It doesn't go down in some mysterious way. Third, this rotation number represents the average amount you go around the circle per time you apply F. So if instead of applying F one time, I apply it K times, I should go around K times as much. And this is true. The rotation number of applying a map K times is K times the rotation number of the same thing. And the final thing is, if I can change coordinates and turn one map into another, they have the same rotation number. So this, having a homeomorphism with this property, this is just a change of coordinates. And if I have a change of coordinates, which turns one map into another, then they have the same rotation number. So this is genuinely an invariant of a dynamical system. So I started off talking about renormalization, and now I've been talking about rotation numbers for, I don't know, 10 minutes. So, so where's the self-similarity happening here? Well, the self-similarity comes from the combinatorics of these rotation numbers. So the key thing here is any real number between 0 and 1 has a unique continued fraction expansion. So I write a number as a1 through a2 in brackets to mean that its continued fraction is 1 over a1 plus 1 over a2 plus 1 over an. And this continued fraction expansion is finite if and only if rho is rational. If rho is irrational, it goes on forever. If rho is rational, it stops. But there's another way I can think about this, and this way is sort of useful for perspective. And this is what I mean by, so I'll explain what I meant by sufficiently irrational earlier. So this is a rational number because the continued fraction stops. But I can also think about it as an infinite continued fractions, except where the next entry is infinity. And then I don't care what comes afterward. And this is because, if I look at this spot in the continued fractions, it looks like 1 over an plus 1 over infinity plus, it doesn't matter what I'm adding. 1 over infinity is 0. So if I allow myself the formal sort of rule that 1 over infinity is 0, I can think about even rational numbers as infinite continued fractions. And so this motivates me to say that, that rho is far from rational if all ai are small. The smaller these are, the further you are from being rational. Whereas if they all get very big, you start to get very close to being rational. And it's one other thing I should note is that there's a good interpretation of A1. So this will be useful. A1 is the maximal n such that rho times n is less than 1. And in particular, if I look at the rigid translation on the circle, this is the maximum n such that applying it n times to 0 doesn't get you all the way to 1. Because, I mean, this is the same expression. That's what I've written here. These two things are literally the same formula. Okay, so if I want to be something that's far from rational, by the way, when I said sufficiently irrational earlier, this is basically what I meant. This is basically what I meant. One way to interpret that is all AI are bounded. The set of AI is a bounded set. So you can ask, what is the furthest I can be from irrational? Well, just make all the AI as small as possible. So make them all 1. And that gets you the golden ratio. This is the least rational number. You'd think that it'd be some awful transcendental number, but no, the golden ratio is the least rational number there is. So this is equal to 1 over 1 plus 1 over 1 plus 1 over 1 plus 1 over, etc. So where's the self-similarity happening in our combinatorics? Well, the self-similarity just means that a part of something looks like the whole thing. Well, this part of this something, if I just chop off the first part, if I chop off the first part that I see, what's left over still looks like the whole thing. This is self-similarity. And in fact, we can do this with an operator. There is a map that acts by chopping off the first element of continued fractions. You can tell that, so 1 over x, it acts on continued fractions by just removing the top numerator. And then that leaves me with the first entry in continued fractions as an integer plus the rest of the continued fraction. And I subtract off the integer part. So this looks like you can sketch this, 1 half, 1/3, 1/4. This is sort of nasty looking function. It looks like a bunch of sort of increasingly sharply downward sloped lines. It's kind of awful, but what we really care about it is that just like sort of from the continued fractions expansion, it's clear that if I put the golden mean into it, I get the golden mean back. So the golden mean is a fixed point of this function. And what will be important for us is that its derivative is actually, oops, not less than 1, it's less than -1. So it's bigger than 1 in absolute value. This derivative is not so hard to compute. This is locally a constant, and so it's just the derivative of 1 over x. So in particular, this derivative is less than -1, and so in dynamics notation, this means that this is an unstable fixed point. This is an unstable fixed point in that if I start near it, I will very quickly move away, exponentially fast. Okay. So I explained, this is some self-similarity in these combinatorics. What does this have to do with self-similarity of dynamics? When you look at this function, this is the graph of the rigid rotation by the golden mean. It's not obviously self-similar. It doesn't scream self-similarity at me. Okay. So in order to sort of continue, I'm going to note when I draw a graph like this, I've actually secretly I've created a special point on the circle, and I had to by drawing a graph. I made the point 0 special. Initially, the circle has no special points, but by picking 0, I've sort of created this graph that no longer really looks like a continuous function. This looks like a discontinuous thing with a big break here at t inverse of 0. And so what I'll do is I'm going to think about this as 2 different functions, one on the interval e1, one on the interval e2. Okay. So instead of thinking about my functions as maps of the circle, let's think of them now as maps from 0, 1 to itself that are broken up into 2 parts. And now we do this sort of cleverness. So in dynamics, renormalization is always about picking a smaller set and looking at the dynamics on that set. And the set that I want is I, 0 going up to t of 0. This is the set that I want to look at. But my problem is that so I want to look at this set. But f of I is not a subset of I. F is not a map from I to itself. But fortunately, for all x in I, eventually fk of I, or fk of x, is in I. If I just make k big enough, if I keep applying f, I do get back to my set. And so this allows us to, what we want to do then is to find a return map. And these sort of things are incredibly common. So a return map is just the map fn of x, where n of x equals the minimum n such that fn is in I. So which iterate I'm taking of my function might depend on the point, and in fact it does depend on the point here. So in this case, our combinatorics is nice, so we can define a pre-renormalization of t, and this is just the same thing as a return map. To be the return map, and there's only 2 cases. So I've drawn it here. This is f squared, this is f. So just to zoom out and look at the two graphs at once, here is my set. This is E1 and this is E2. So notice that the bottom graph is not from 0 to 1. It's just from 0 to 0.6. I've restricted this graph to a smaller set, and on it on the right, I act as f, because f there genuinely stays inside of my set I, whereas on the left, I had to apply f twice. And what I claim, so this is a weird concept. What I claim is that this kind of looks kind of similar to what I started with, right? I mean, it doesn't look the same, but it looks kind of similar, right? Like when you look at this graph, like it still kind of matches up here. It still kind of matches up here. This still kind of looks like a circle map, at least, in these two pieces kind of way of thinking of them. But there are some differences. So by the way, so in terms of what I was talking about earlier, this is the rescaling. This is the rescaling. So now what I need to do is normalize. So there are two differences. One is that the obvious one. The domain is smaller. I started with maps on 0, 1. This is not a map on 0, 1. It's a map from 0 to 0.618. So I need to make the domain bigger. And two, look at my initial map. My initial map, the left half is big, the right half is, or the left half is small, the right half is big. In this map, the left half is big, right half is small. So here, the left half is bigger than the right half. So for my purposes, both of these things are problems. So I'm going to choose my normalization to be that my function should be defined on 0, 1, and that their left half should be smaller than their right half. So we can actually fix both of these problems at once by conjugating by an affine map. So basically, all we want is we want to pick an L. We want to pick L. L sends sends I to, I'll just write out, since 0, f of 0 goes to 0, 1, and I want it to switch orientation so that it switches these two sets, it puts the smaller one on the left again, and I want it to send the endpoint to the endpoints. So 0 ought to go to 1, and f of 0 ought to go to 0. So I want it to switch the endpoints in reverse orientation, and I want it to scale up the thing to the whole size. You can actually just find this map explicitly. This map is L of x equals -1 over f naught x plus 1. It's just a linear map. And now we can define our renormalization operator. So ignore the text above for the moment. Our renormalization operator is our return map. And then before we apply it on 0, 1. This shrinks us down to our little set. Then we apply the return map, and then we grow back to the full size. But
sorry,
yeah.
A question, and
Yep.
maybe I just missed your explanation of this. Why are you flipping the orientation here? Why don't you just linearly scale with your normalization?
Yeah. I mean, there are a couple of reasons for this. Oops, my screen's flipping out a bit. Sorry. I mean, so it does seem a little bit silly that I chose my normalization to, like, why do I care which half is bigger? The reason for this is the reason for this, I mean, there are a bunch of ways to think about this. So what's sort of really happening here? So let's think about my interval 0, 1. Okay. So what happens when I apply a rigid translation to this is I get a sequence of points. And so what renormalization is really doing is I'm looking at the last, so here's t of 0, here's t squared of 0, here's t cubed of 0, here's t fourth of 0. I mean, in this case, we don't have this many iterates, but this is the last time before tn of 0 crosses 1. And then what I'm going to do is I'm going to repeat this operation, but I'm going to think about instead I'll end up my next map will be going the opposite direction. This it's a weird thing to explain. I mean, the other way to say this is that I wanted it to be true that that my map was like close to this golden mean rotation. The golden mean rotation goes more than halfway when you first apply it, and if you go more than halfway, then looking at this first graph, then this difference should be bigger than 0.5. And if this difference is bigger than 0.5 and the slope is 1, then the left is smaller than 1/2. Perhaps that's the easiest way to think about it. There are a lot of different pictures for this, some more intuitive than others. There is one thing I haven't explained though, which is what is this condition doing here? What does this have to do with this being 1? So I've sort of ignored a detail when I did this, which is when I started out here, I drew these 3 points: 0 less than t inverse of 0 is less than t of 0. And the thing is, actually, this procedure doesn't work unless you have this condition. And not every map satisfies this. So I need to assume that this holds. And if I apply t to it, then I get t of 0 is less than 0 is less than t squared of 0. And what this means in its own language is that when we apply our map, the first time that we cross 0 is between the first and second iterate. And so this is equivalent to saying that rho f or rho t, oops, no, go away tablet, is 1, a2, a3. Establishing this condition tells us that we cross 0 after 1 iterate, or after 2 iterates, but not 1. And so remember, when we define continued fractions, oh God, stupid tablet. When I defined continued fractions, I said the first entry in continued fractions is the maximal n, which is before you can cross an integer. Okay, I'm very short on time. Let me try to really quickly ask. Okay, well, I'm shorter on time than I expected, so here we go. Anyway, let's write out what this does. I've written out a formula, right? But this is really hard to think about. So let's explicitly calculate what this thing does to pure rotations. So when I'm thinking about a pure rotation in my sort of piecewise way, if x is small, then it's still a map from 0, 0, 1 to 0, 1. But if x is big, then x plus rho is bigger than 1, and so I need to subtract off 1. So this is my way of thinking about a map in 2 pieces. Pre-renormalization, so pre-renormalization of t rho, well, it's t rho squared if x is between 1 and rho, 1 minus rho, and it's t rho applied once if x is bigger. So this is just me writing down a definition, the definition of renormalization. So let's apply this. Well, the bottom case is easier. This case falls in here. So the bottom case is x plus rho minus 1, provided 1 minus rho is less than or equal to x, less than or equal to rho. The top case, well, the first time I apply it, t rho, it's in this case. So I get x plus rho, and I need to apply t rho again. But now, once I've added rho, rho is bigger than 1 minus rho by my assumption. So now I'm in a second case. So I get x plus 2 rho minus 1. Okay. So what I'll note here is that this does not look so different than what we started with. The only thing that's, the x dependence isn't more complicated. It's still like this linear pure rotation. The only question is, how much does this rotate by? How much does this rotate by? So, and what I claim is that, well, notice that this is defined on a domain from 0 to R. So all L does is reverse orientation and dilate by -1/rho. The minus for reversing orientation and the 1/rho to make this size 1. So if I conjugate by this, I claim it doesn't actually affect the x's at all. And all it does is it multiplies these numbers by -1/rho. And it switches the order of these two cases because it's reversing orientation. So the case on the right, the case on the bottom, which was the case on the right, becomes the case on the left. So right on the top. So renormalization on T rho of x becomes x plus, on the bottom case, I multiply by -1/rho. So 1/rho minus 1. On the top, I multiply by -1/rho, x plus 1/rho minus 2. And let me rewrite this as -1 minus 1. Notice this is just like the expression we started with, except that I'm not adding rho anymore. I'm adding this. So this is a pure rotation. This is a pure rotation by 1/rho minus 1. And I claim that that this is actually equal to the Gauss map of rho. This is actually equal to the Gauss map. In particular, because 1/rho floor is equal to 1. So let me, and I have 2 minutes, so let me end by going over the big theorem. The big theorem, and this is sort of like a theorem that provides a picture. I'll try to draw the picture. This theorem applies in almost any case where dynamics appear, where renormalization appears in dynamics. So first off, renormalization has a fixed point. The fixed point is the rotation by the golden mean. And it's the only fixed point. The second thing is its derivative there has one unstable eigenvalue, and that eigenvalue is equal to the derivative of the Gauss map. In particular, it's unstable because it's less than -1. All other eigenvalues lie strictly inside the unit circle, so every other direction is stable. In particular, it's hyperbolic. It's also a compact operator. So in dynamics, hyperbolicity is important because it gives us stable and unstable manifolds. So an unstable manifold is the set of F such that R minus 1 of F goes to T phi exponentially fast. So this is the set of things such that the pre-images converge to the fixed point. So in backwards time, it goes towards the fixed point exponentially fast. So in forwards time, it goes exponentially fast away. The stable manifold is the same thing, except in forward time. So it goes towards T phi exponentially fast. Okay. So I claim that we have a one-dimensional unstable manifold, which is analytic, and a codimension 1 stable manifold. And the picture here is this. Here is our fixed point. Here is our unstable manifold, which moves away from the fixed point. Here is our codimension 1 stable manifold. If I start on this, points flow in towards the fixed point. And if I take some arbitrary family, F lambda, a family of circle maps, well, provided this is what's called full, which means that basically we say it's a full family, and all that means is it starts below the manifold and ends. It starts below the stable manifold and ends above. Well, because it's codimension 1, everything that starts above it, or starts below it and ends above it, must cross it at a single point. F lambda star. And the point of all of this, in some sense, is that if I apply renormalization now to this family, what will happen is that the point that's in the stable manifold will move in towards the fixed point, and everything else will get stretched out and stretched out even further, so that the whole family will converge onto the unstable manifold. But the fixed point will, or the point in the stable manifold will converge in on this fixed point. So I'd love to say more, but I think I'm out of time. So so this picture is called the Wilson-Kadanoff picture, and it comes from statistical physics, which is sort of the origin of this way of thinking about renormalization, the theory of phase transitions. Okay, so that's it. Alas, I didn't get to use it to prove anything, but.
All right. Does anyone have any questions?
So were Wilson and Kadanoff the ones who proved this theorem you just said?
No, Wilson and Kadanoff are both physicists, so they weren't proving anything. But this particular picture, in the diffeomorphism case, I would almost say that this theorem is folklore. I'm not even sure who proved it. You can draw a similar picture in a lot of circumstances. So if there's a similar picture, for example, for maps of the circle with one critical point. So instead of diffeomorphisms, things with one critical point. And that picture comes from Yampolsky, or Misha Yampolsky. But this, in the diffeomorphism case, I'm not actually sure who proved this first. Yeah. So if you have any other questions about renormalization, or you want to hear about how it works in physics, let me know. I'm always happy to talk about it.
I think final round, this construction only works for at least the example earlier, when the first entry is just 1, isn't it?
Yes.
But when it's like 2 or greater, you can modify it somehow. The same theory works.
Yes. Yeah. So the construction, there is so if you notice, whenever I wrote R, I wrote this little subscript 1. And the reason for that is that there's actually a family of these operators, one corresponding to each first possible entry in the continued fractions. So the one corresponding to 2 has a fixed point with rotation number, 1/2 plus 1/2 plus 1/2, and so on. The definition of all of them is similar, although it is harder to prove things about the higher ones, simply because if you're iterating a map more times, it kind of behaves worse. So this one is sort of the easiest and nicest one.
All right. Any other questions? If not, then that's it. All right. Thank you so much, Matt. Okay. I'll see you guys next week.